All right, welcome back. In this video, we're going to start to look at Newton's method. If you follow the notes, you can kind of see the idea behind Newton's method. Your textbook on page 265 kind of is a visualization of how Newton's method with refined estimates over and over shows you how it gets closer to the zero as well. So we're going to kind of begin here with the understanding that you read through about Newton's method. Now we're going to see how to execute it. So in this problem here, we're given a basic polynomial, which we can find the zeros, the x-intercepts of this equation, without anything special. It's a basic polynomial. We know that they're positive 2 and negative 2, but we're going to choose this as a starting example because it's really basic and easy to work with, and we can see how Newton's method does actually work. For refreshment, Newton's method is your next guess, is your initial guess or your current guess, minus the function evaluated at that guess divided by the derivative evaluated at that guess. So the first thing we're going to need to do here is we're going to need to compute the derivative. Well, f of x has a pretty easy derivative. All right, it's minus 2x. And then we need to make an initial guess. Now I know the two zeros are positive 2 and negative 2. Now, one of the things you want to be really careful of with Newton's method is trying to avoid guesses where the derivative is 0, because that would cause division by 0, and that could really mess up Newton's method. So, have that in mind and be aware of that. Okay, so we're going to make an initial guess of x0 equals 1. So the way that formula works is your next guess would be x0 minus f of x0 divided by f prime of x0. And so here I've substituted in for the derivative here f prime and for f, putting in that value x0. In this case it's 1, so I'm just going to plug that in. So that's going to be 1 minus 4 minus 1 squared over negative 2 times 1. And what we're doing here when we do this is we're actually finding the x-intercept of the tangent line. The x-intercept of the tangent line that passes through that point. That's where the derivation of Newton's method comes from. And then we compute that, and we get 2.5. Okay, 2.5, if you compare it to the actual 0, which we're around here is x equals 2, 2.5 is closer than x equals 1. And so then we take that guess of 2.5, and we're going to repeat this process over now. Instead of having x0, now we have x1. So when we come to x2, it's going to be x1, which is 2.5, plugged into that formula, f of x1 over f prime of x1. So 4 minus 2.5 squared over negative 2 times 2.5. And again, we compute that, and when we do, we get 2.05. So now we're even closer to the actual 0. And this is the idea, again, it goes back to that graphical idea of you're chasing the tangent lines in the hopes that they're getting closer to the actual 0 where they cross. And so we're going to do this one more time by hand, and then I'm going to explain how you can use technology to actually help you do this a lot quicker once you get it set up. So we're going to take that 2.05 and plug it in. That'll be 2.005. Oops. Looks like I made a typo. Hold on one second. Okay, so now we have it fixed up to be 2.05. I had written down too many zeros when I first wrote that out. And so now we just compute that, again, using a calculator. Be careful when you're typing that in a calculator. Make sure I have grouping symbols around the numerator and denominator. And when we do, we see that we're even closer to what we know the 0 to be, which is positive 2. So now we're at 2.00, rounding off here, 61. And we could keep doing this by hand, and the way Newton's method works is it's just going to keep getting closer and closer until we get within whatever level of tolerance we find acceptable. Nearest thousandth, nearest millionth, how close do we need to be? It is an estimating method, so sometimes you do have to accept that you're going to have an estimate of the 0, not the actual 0. Now, what I want to talk about is how you can use your calculator. So if you have a graphing calculator, this works with Texas Instrument graphing calculators. It works with Casio graphing calculators. is we're going to begin by putting in our initial guess. And the way we do that is we put it in as one arrow X. That uses a button on your calculator called the store button. It looks like stow with a little kind of arrow pointing. So that's the symbol you use for the 1 and for X. So we put the initial guess into the X variable. We then type in our expression X minus f of X over f prime of X. We use the arrow again to store that new value into X. This leverages the calculator's variable capabilities. What it's doing here on the right-hand side of the arrow is that's saying put it into this container. When we use that container, that variable on the left-hand side, it's actually looking up and getting the value. So it's finding a value, finding a value, finding a value, and then putting that value into that container X. Now, in our particular example, you have to actually put in what f of X and f prime of X is. In our particular example here, we're using 4 minus x squared over minus 2x. We put all that stuff in, and then we use the store button to put it back into X. And at that point, then we just continue hitting the enter button. Because each time we hit enter, it's going to take that new value, our new answer, plug it back in, get an answer, put it into the container. So if you don't have a graphing calculator, you can use the calculator that I have here. It works. It's a little bit different. This is a Power One app. It's actually a free download. I purchased extra things, so mine's paid for, a paid one. But the basic one should work. So what you do on this calculator, if you're using it, and you can kind of follow around if you have a graphing calculator, check your answers, is you would put your initial guess in, just type it in and hit enter. You then type in the formula here. Now I have to use my last button because I don't have a store button, but I put in last instead of X, so last X minus the numerator in parentheses 4 minus X squared, 4 minus last squared, divided by negative 2 times last. I don't have to do a store because that just pulls the last answer. And then I can just hit equals. You can see there's the 2.5 we got. And if I pull that answer up again, now it's going to take my last answer, which was 2.5. And it's going to compute it, 2.05. See, same thing we got. Compute it again, 2.0061, just like we found rounding off. And we can keep doing that until this levels off to something. Now your calculator might go a little longer than mine because of the storage capabilities of your answers. So here I get that one, and then if I do it one more time, I think my calculator then just levels off flat to 2. The answer is 2, of course, we know. And so that's Newton's method, and that's kind of how you use your calculator to do it. Again, if you don't have a graphing calculator, you can definitely download this app. It's called Power One, and you can do that using that last button like I did in this example.